Right, well, the goal of this lesson is to learn about direct proportion and solve some related problems. So please pause the video as you go, taking notes and completing the examples as usual, making sure to show all you're working out. So we're going to be looking at direct variation, and that occurs when two variables are directly proportional. An example of that, imagine you were going to the shop to buy some lollies. The number of lollies you can buy varies directly to how much money you have. If you have $1, you might be able to buy 5 lollies. If you have $2, you can buy 10 lollies. If you have $3, you can buy 15 lollies. So the number of lollies you can buy is directly proportional to the amount of money that you have. Now, there are a number of dot points here, and I'm going to come back to them at the end because they're a little bit tricky to understand until you've seen them in practice. But the main thing here is that when you have two variables that are directly proportional, you can write one as a multiple of the other. So either y equals mx or y equals kx, either of those. And so let's have a look at the first example. We'll come back to those dot points later. A train travels at a constant speed. The distance d the train travels is proportional to the time t traveling. Write down a formula using a constant k of proportionality. Okay, big word, but all it's saying is write down the equation, and we know that the distance, you'll notice back in the question here, I'll highlight it, the distance is d and the time is t. There are two variables. So the distance is equal to k times time. D equals kt. We've used the constant k that they've asked us to. So that's like a little equation that will tell us how far it goes given the time. Our only problem is we don't know the value of t. We would need some more information. And so that's what we're going to get in part B. If the train travels 340 kilometers in 4 hours, find the value of k. Okay, so given that information, we can say that when t equals 4, the distance is equal to 340. Substituting that into the equation above, I'll highlight it now, just up here. Substituting the values that we know into that equation, we get 340 is equal to k times t, which is 4. K times 4 is just 4k, and that's equal to 340. Solving that as equation, we get k equals 340 divided by 4 is 85. So k is equal to 85. That allows us now to write down a formula for the distance in terms of the time. So using the highlighted formula at the top of the screen there, we have distance is equal to k, and we're going to write the 85 now where k is because we found what the value of k is, 85 times t. There is our formula for how far the train will travel given time t. And it's worth noting that the units are kilometers and hours there. We need to make sure we know that so that we can answer questions from that. Okay, find the distance traveled after 5¼ hours. Okay, so when time is 5¼ now we can write that as a fraction or as a decimal. I might write it as a decimal, 5.25. The distance, substituting it into the formula above, is going to be 85 times the 5.25. And if you calculate that, it comes out to be 446.25 kilometers. How long does it take the train to travel 119 kilometers? Well, we'll go to the formula again. Our formula is distance equals 85 times time. This time, we're going to put the distance equal to 119 kilometers. And so we get 119 is equal to 85t. Solving that for t, divide both sides by 85, 119 divided by 85. And if you calculate that, you get 1.4. You could leave it as a fraction. But what's nice is if you hit your degrees, minutes, seconds button on the calculator, that will tell you that it's 1 hour and 24 minutes. It converts it to hours and minutes, just like it did when we were doing trigonometry. Okay, draw a graph of the distance traveled against time, and you'll notice we've been told to take time to be between 0 and 4. So we take time to be our horizontal axis, and that is going to be in hours. That was the unit we were given for time. And the distance up the vertical axis is going to be in kilometers. Now, all right. Now we want from 0 to 4. My scale is probably not the best here, so I'm just going to move that up a little bit, just out of the way, because I actually want to go to 4 here. So I'm going to just fix up, oops, just going to fix up the top of this graph if I can without causing too much problems. Okay, so that's going to be 4 high. I'm going to go across here. 1. Shall bring that back a little bit. 1 hour, 2 hours, 3 hours, 4 hours. 1, 2, 3, 4. Now I'll put a dot at the origin there, because when you have no time, the train won't travel at all. After 1 hour, if you put 1 into the formula, d equals 85 times 1, which will be 85. So this will be 85. In fact, you can see it's going 85. Every time you go up 1 for time, you'll add on another 85 kilometers, which makes sense. You're going essentially 85 kilometers per hour. That's the rate at which the distance is changing every time time goes up by 1 hour. So if I go up by 85 kilometers each time on my y-axis here, plus an 85 gives me 255, and then this one will be 340. After 1 hour, it was at 85. After 2 hours, 2 lots of 85 is 170. 3 lots of 85 is 255. Now you'll have a ruler, so try to keep yours neat. I'm doing mine a bit by eye here, and I think that last one might be out. We'll see. And then once you've plotted those points, we're going to draw the line through those that represent, it's not too bad, the line through it that represents the distance that the train is traveling against time. It's always good to write your equation. So it's distance equals 85t. And I might just call this train travel, so we know what it is. All right, so there is a graph of distance on the y-axis traveled against time, which is on the x-axis. Use your graph to estimate the distance traveled in 1.5 hours. Okay, so what I'm going to do, it says to estimate, right? So we don't have to calculate. We're going up from 1.5, and we're going to go across here and estimate where it is. Okay, now it looks to be halfway. So I could take the average there of 85 and 170, and if I do that, I get 127.5 kilometers. That's what I would say there. Now, that happens to be the exact amount, but because it says use your graph to estimate, if you were off a little bit because your line didn't come out looking right in the middle there, and you said 125, 130, that's likely to be accepted. We'll see an example of that here, because with the next one, the time taken to travel 200 kilometers, if I come back from 200 kilometers, and I've got to guess where 200 kilometers is on this. So I reckon it's somewhere in here. And so I'm going to go across from there till I hit, try and keep it horizontal there, till you hit that line, and then coming down from there, come down to that point. So I reckon it is less than 2.5. It's probably closer to 2 1/3, maybe slightly more. This is where it is an estimate, and it's okay that it's an estimate, and you will be given a bit of leeway. So for me, I'm going to guess that it's close to 2 1/3, so 2 hours. 2 hours. Oops, if I can get my pen to work. 2 hours 20 minutes. You could calculate the exact, and I'll tell you that the exact is 2 hours, 21 minutes and 10.59 seconds, but there's no way you'd be able to be that accurate reading it off the graph. Okay, example 2, the mass of a steel beam is directly proportional to the length, right? The mass M is directly proportional to the length L. There's your two variables. We're also told that when the length is 50, the mass is 8. So find a formula linking the mass and the length of the beam. Okay, so a formula linking the mass and the length of the beam. So we're going to start by writing down the fact that the mass is going to be a multiple of the length, just like we started in the last question. M equals K times L. And we've been told that when the length's 50, the mass is 8. So when the length is 50, the mass is 8. And I'll write that down. When L equals 50, the mass is 8. And we're going to have to remember the units are in centimeters and kilograms. And so we've got, substituting those numbers into the formula, 8 equals K times L, which is 50. So K is equal to, if I divide both sides by 50, it will be 8 on 50, which of course simplifies to 4 on 25. And so therefore, the mass is equal to KL, which is 4 on 25 times L. Okay, I'm substituting it back into this equation. I'm underlining in red here. I found my K value, I'm putting it in there now. Now I could leave it as 4.5 times L, but it would also be possible to write it as M equals, it'd be also possible to write it as M equals 4L on 25. Okay, so there's our formula. Find the length of the beam when the mass is 850 grams. Now we have to be careful here. This is in grams, and yet the question is linking centimeters and kilograms. So we're going to have to change that to 0.85 kilograms when we substitute it into the formula. So we know that when the mass then is 0.85, substituting the formula, we get, sorry, I'll just change that. We get 0.85 equals 4L on 25. All I've done is gone back to the equation. I'll highlight the equation now so you can see it. I've gone back to the equation that we had, and I've substituted M equals 0.85 into that equation. And I'm going to solve it for L. So I need to multiply both sides by 25, and so that will give me 4L equals 21.25. And then I'm going to divide both sides by 4, and we get 5.3125. And what is the units? Coming back, you'll see at the top of there, question 2, when the length is 50 centimeters, so our units are in centimeters. So this is centimeters. So that's how long the beam would be if it weighs 850 grams. Okay, let's have a look at another one. The cost C of driving a car at 60 kilometers per hour is proportional to the distance d kilometers. Okay, so notice again, we're comparing two variables, C and D, the cost and the distance. And we have to find, it goes on, tells us how many litres it uses per 100 kilometres and how much petrol costs. Find a formula for the cost in terms of distance, and hence find the cost for travelling 185 kilometres per hour. Okay, find the cost in terms of distance. Okay, so notice that we have 6.4 litres per 100 kilometers. And if we do 6.4 times $2.50, that will tell us how much it costs per 100 kilometers. So 6.4 times 2.5 comes out to be 16 per 100 kilometers. Okay, so we now have a cost in terms of the distance. All right, now we know that for the car, the cost of driving the car is proportional to, so the cost is a multiple of the distance. So there's our formula again. I've put our K in. Could use an M, but we're choosing to use K here. C equals KD. All right, and so now we're going to say that when the distance is equal to 100, the cost is equal to 16. And so putting those values into your equation, you get 16 where the C is, K we don't know, times 100 for D. Dividing both sides by 100, because it's 100K equals 16, we're going to have 16 divided by 100. Now, I'll write it like this, but obviously you could change it to a decimal straight away if you like, or you can leave it as a fraction, but I would simplify it. So the K value is 0.16. So sometimes we leave them as fractions, sometimes we put them as decimals. And so I now finish with the formula. Remember, we're trying to find the cost for traveling 180. We're trying to find, the cost for traveling 185 kilometers. So the cost now we have found is 0.16. That's the K value times D. So when D equals 185, the cost is going to equal 0.16 times 185. And when you calculate that, 0.16 times 185 comes out to be a cost of $29.60. That's how much it would cost to travel that far. All right, and part B, find the distance in terms of cost, and hence find the distance that can be driven for that amount of money. Okay, so find the distance in terms of cost. So we had before that, if I go back to our formula, we had our cost was equal to, okay, where is it? 0.16D. So if I want the distance, if I divide both sides by 0.16, will be the cost divided by 0.16. So there is a formula. I've changed the subject of that formula to be D. So there is the distance in terms of the cost. All right, so now I can answer the next part of the question. When cost is equal to when the cost is equal to 14.75, that's how much money we have to spend on our petrol, the distance is going to equal 14.75 divided by 0.16, which comes out to be 92.1875 kilometres. So that's how far it can be driven on $14.75. Okay, a couple of last questions here. From the graph, find the rate of change of distance over time. Okay, so rate of change of distance over time. Here we have, you'll notice, for a time of 1 hour, the distance goes up by 10. In fact, every 1 hour you add, the distance goes up by 10. Cross 1, up 10. That's just like our gradient that we studied in a previous lesson. So here, the rate of change of distance is 10 kilometers per 1 hour. And of course, we could write that as 10 kilometers per hour. That is the rate it's changing, 10 kilometers every hour. In the next question, find the rate of change of height over time. So here you'll notice that every one across we go up 5. So 1 across, up 5, 1 across, up 5, 1 across, up 5. Now, there is no units on the height here. So we're just going to write units because we don't know if it's meters, centimeters, kilometers, or what. I've given us minutes on the horizontal axis. So what we're saying is it's going up 5 units per minute. So there it is as a rate. That's the rate of change of the height over time. 5 units per minute. All right, now these are the exercise questions I'm going to be getting you to go on with from exercise 4E at the bottom of the page there, but I'm just going to pop back to the top now that we've done some examples. So if you have a look at this, I'm just going to go over this. The first dot point says the rate of change of one variable with respect to the other is constant. Let me just explain that. Let's go back to the graphs at the bottom there. You will notice that there is a constant change. Every one that you go across, I'll put the numbers on, every one that we went across, we went up 10. Every one that we went across, we went up 10. Every one, 10. It's a constant. It's not changing how much you go up. You are always going up 10 every time you do one. And it was the same with the graph below. So direct variation, with direct variation, and direct proportion, which basically means the same, you have a constant change. The rate of change is a constant. Okay, rate of change is constant. The graph is a straight line passing through the origin, and you've seen that. When we graph them, there will be a straight line passing through the origin. We know the rule. We've been using the rule. You can use either y equals mx or y equals kx. And the gradient of the graph is equal to that rate of change. I'll show that on the graph below, but just quickly first, that last dot point, the letter M or K is called the constant of proportionality. Big word, but that we sometimes refer to that as a constant of proportionality. Let's just go back to the dot point before. The gradient of the graph is equal to the rate of change. So if I just go back down to this graph where we were studying the increase here, notice that this is the gradient of the line. Remember, gradient is equal to the rise divided by the run. And every time you go a run of 1, you are rising 10. And so the gradient is the rate of change of that line. All right, so you can now go on with the exercise questions